All right, can folks on YouTube hear us okay? Let me double check. Yeah, looks like we're good. All right, welcome everyone to another episode of GP Mode. This is like lecture 57. And today I'm really thrilled to have Cris Cecka, who's made a few cameos in a few of our past lectures. Cris is the creator of CuTe, and so he's here to sort of teach us basically everything we need to know about like tensor algebra. I'm also joined by one of my friends and colleagues, like Cris, who does a lot of CuTe attention-y related stuff in PyTorch, and might also have a lot of questions. So yeah, so Cris already told us before the cameras got rolling, he loves questions. So please, if you have any questions, drop them in chat and we'll interrupt him. So yeah, without further ado, Cris, please take it from here.
Okay, thanks, Mark. So I am Cris Cecka. I am the original inventor of CuTe, and I wanted to come on here and kind of tell you the story of CuTe and tell you how it works. And so CuTe stands for CUDA tensors. And let's jump right into it. I'll give you a quick history. I have a big history in numerical linear algebra. I was doing a lot of, for example, FFT research. And for the FFT research, I needed BLAS extensions for tensor contractions. Tensor contractions were difficult to do, and I didn't understand why. Why did they have to be difficult to do? Sorry, this is messing with me. There we go. BLAS extensions were, tensor contractions were difficult to do, and I didn't understand why. I moved on to some low-rank machine learning research. This, for example, is a Kronecker product of two canonical polyadic decompositions, which is my favorite tensor decomposition. But again, tensor contractions were hard, and I didn't understand why. Like, why can't I just have my tensor contractions? Tensor contractions are just GEMMs. So I started poking around inside NVIDIA, like, what could we do about tensor contractions? And I collaborated with Paul Springer for a very long time. He was building CU Tensor at the time, and encountering a lot of Cutlass 2 pain. I understood some of that pain, and I still didn't understand why this is hard. Like, this seemed like the most obvious and simple thing to me. So I started building CuTe. And I applied CuTe to Volta, Ampere Hopper. A really amazing intern, Mohammed Osama, came along. And I knew I was onto something when in the first week of his internship, he was able to grok just a single file CuTe example for a speed of light gem, modify it, and beat cuBLAS by 25%, which was unheard of, because at the time, GEMMs in NVIDIA were pretty much being built from assembly directly, and having an actual hackable single file C code, C++ code gem that you could hack and modify and do something interesting with was amazing. So we kept going. We implemented what's called StreamK, published a paper. Tensor cores. This is my favorite tensor core. I finally applied CuTe to actually doing the tensor contractions that I initially started with, and was able to get SOL and show off a bunch of things. That got Cutlass's attention, and then VJ, who I nicknamed the Golden Intern, took these ideas and ran insanely fast with them, and helped to build out this Cutlass 3, which covered Hopper, Blackwell, TMA, and yeah. That's kind of the story of CuTe development and CuTe history. What is Cutlass? Cutlass is a set of abstractions for productivity and performance for all scopes and scales of building dense linear algebra for GPUs. It's multi-level. You can enter it at different at any one of these layers. So we have full SOL. SOL inside of NVIDIA stands for speed of light. Speed of light is as fast as a certain chip will go. We can calculate how fast we can possibly go using a certain architecture. and that is the speed of light to us. If you hit that speed, good job. If you don't hit that speed, if you're 1% off, let's go find that 1%. We need to go the speed of light. We have to go as fast as we possibly can. So Cutlass presents a bunch of speed of light kernels. If you're just interested in a GEMM, we have a GEMM, and you can stamp that out and run it. If you want to start hacking a little bit, you can get into the collective layer. If you want to start hacking even more, you can use CuTe. Everything inside of Cutlass is implemented in terms of CuTe, and I'm going to show you some of that base level stuff. Inside of here, there's CuTe examples, which are really actually these kind of bare naked single file GEMMs that serve as examples, both to internal NVIDIA engineers and to external people that are interested in CuTe. And it shows you how to use some basic operations. And then over 100 Cutlass examples now, I believe, that cover everything from tensor contractions, convolution, fast attention, multi-headed attention, group GEMM, FP4, stream K, epilogues, distributed GEMMs, optimizations on top of optimizations. It's amazing. This is the most popular NVIDIA open source project, period, hands down. It's got 4.2 million downloads per month, 7,500 GitHub stars. This is a wildly successful project, and I am ecstatic to be working on it. This next slide I copied from a presentation at GTC, and I have never seen it before in my life. So let's take a look at what this says. Major pain points with C++. C++ templates are inconvenient. Oh, this feels like a personal attack. Additional mental load when writing compile time logic. Error messages are longer than novels. Whoever wrote this doesn't read. They don't like reading. They don't like full information in their error messages. C++ templates suffer from slow compilation time. Sounds like a skill issue. Front end too generic for our purposes. Wow, okay. Anyway, I'm a C++, I can, my code's compiling, it takes forever. I can fix this slide real quick, I think. There we go. Okay. So I am a C++ fanboy. I grew up in C++. C++ has an amazing architecture model and computer model. But I agree. C++ is hard. It's slow to compile. People have complaints. That's okay. Because we just introduced Cutlass 4.0. All of the things that I'm about to show you, we have this cute little Python here reading a cute DSL book. And so all the things I'm going to show you in this talk and all the things that I talk about in this talk are now ported to being done in Python. And the benefits of that, of course, are integration with things like PyTorch and all of your ML kernels. Of course, more benefits are included in blazing fast compile times. So over 100x improvements in compile times. C++ has a hard time with that. And you can just start writing CuTe kernels in native Python itself. So this is a hello world, and there are a ton of resources if you go to the NVIDIA Cutlass GitHub repo. Lots of documentation, lots of new examples. I would highly recommend checking it out. But I'm here to talk about CuTe. Everything that I say here should also apply to Python. If it doesn't, let us know about it. We would like to know. But what is CuTe? CuTe in a slide is two things. CuTe layouts are a representation. It allows us to express data layouts that go far beyond row major and column major. And they let us write extremely generic algorithms like copy, gem, reduce. We only need to write these once. They allow us to encapsulate metadata. I'll explain what that means later. CuTe layouts are also an algebra. What does that mean? It means I can combine layouts to create new layouts, and I can implement way more generic tiling and partitioning than I have ever seen before in any other system. So let's see how some of this works. So the way that I think about CuTe, okay, let's talk about loops first. If we consider this arbitrary for loop and I wanted to essentially represent this for loop, all of the parameters of this for loop I could write down inside this box, right? The for loop starts at 2, it ends at 50, it increments by 3, it has a base pointer of A, and it does this weird index transformation inside of the loop. That's complicated to me. But an exactly equivalent code can be written like this, just by transforming the for loop starting position to 0, transforming the for loop increment to 1, and then performing some index math on the base pointer and transforming the any index transformations that are inside the loop. And this, I claim, is much more interpretable, because now I can immediately say that there are 17 elements inside of this that I'm modifying. Those 17 elements are all strided away from each other by 21. And those 17 elements start at this particular position in memory. Just by glancing at this for loop and these parameters, I could not tell you that, right? We can derive it, of course, but I could not just immediately tell you that. So this is a 17 element vector somewhere in memory with whose elements are strided away from each other. We can do the same thing for 2-dimensional loops, right? This is not constrained to 1 dimension. So for a 2-dimensional loop, right, the parameters start exploding very, very quickly. But again, we can transform it so that the base index is 0, the increment is 1, all the transformations are happening inside the loop, all the constant offsets are accumulated into the pointer. And so we just have a base pointer. And here it looks like we have a 2-dimensional object, which is taking 2 indices that one of those indices iterate to 4, and one of those indices iterate to 20. So maybe we could interpret this as a 4x20 matrix. And then it's got some strides, which tell us where the elements of that matrix actually live. Again, by just looking at this code, I couldn't really tell you those things. I couldn't tell you what's going on here. So by simplifying the shapes that we're looking at, by simplifying the base pointers that we're looking at, we can start talking about building this layout object, which is going to be a mathematical function, which tells us how to map logical matrix coordinates to physical value indices. And this is not new. It's not particularly interesting. And so, for example, if I have a 2x3 matrix, I can represent that in column major. Okay, and I'll list out the strides explicitly. So the strides as I go down this first mode of size 2 is the stride is 1. So A, D follows A, E follows B, F follows C, as you can see in the physical representation. Row major is the opposite. The stride 1 just appears in the other mode. We can immediately, generalize this. There's no reason why I have to use 3 here or 2 here. I can stride by 4. This gives me a padded column major. So the actual values of the matrix live here in these positions in memory, and the other positions in memory are just dead space. They're just not used. Okay, that's fine. This immediately extends to tensors as well, right? So if I have a rank 3 tensor, I can give each one of those modes independent strides, and that will tell me where these elements live in physical memory again. In general, if I want to know, if I want to map from my logical coordinate to my physical offset, then I just take the inner product of the coordinate with the stride that I have. Does that make sense to people?
So Cris, a lot of the insight here is like all of these sort of like mapping from logic to physical. The constraint is always like this is an affine function, right? And so like I guess like are you also suggesting that like this is the only kind of useful transform? And I guess you made a face, so maybe you disagree with me. I'm curious. Yeah.
So I agree. These are all affine transformations, and those happen to be the most useful and the most common. They are not the only transformations that you could imagine. Triangular matrices, if you wanted to do those. You could not have any memory at all. You could be looking up, you could be computing values on the fly. You could be doing lots of things with this layout. These are the most common. These are the ones that people like to start with. Row major and column major. I think everybody's implemented something like that at one point. But to that point, I do think of CuTe as a generalization of these kinds of really common patterns. So for example, MD span. I compare CuTe tensors to MD span very often. But I would also claim it's much, much, much easier to use, at least for all of the very common applications that we're going to be talking about, which do happen to be affine. You can do fancier things in CuTe. I'll touch on it if we have time, but yeah, we'll focus on these first. So if you're familiar with StudMD span, I don't like its interface. I don't like a lot of its abstractions. And I should just be able to create what I call a layout. It has a certain number of rows, a certain number of columns. Give me an iterator to whatever data you want to actually back this tensor with. Give me a layout that describes this coordinate to index mapping. And then we're off to the races, right? We can have our double for loops. We can index into our matrix and set it to whatever we want. We can assert that the rank of this matrix is 2, right? I gave it 2 modes here. Cool. Yeah. Tensor is a view, not a container. It can take any kind of iterator that you want. The rank is the number of modes of a tensor, sometimes called the number of dimensions of a tensor. Like a matrix is rank 2, a vector is rank 1. The size is the extent of a mode. So here we're just asking like what the size is along the 0th mode. What is the size along the 1st mode? And the stride is the elements. It is the elements between the consecutive elements. The cool thing about CuTe, the first thing I did in CuTe was that very, very often I know what these values are, either the shapes or the strides. I know what those are at compile time. And I don't want this integer to require any storage in memory or require any compute at runtime. So you can just replace these dynamic integers with static integers. This int22 is a static integer. Didn't change any other code, still just going to make a shape out of the static integer and the dynamic integer. We can still assert that this is a rank 2 matrix. We can now static assert that the size of the 0th mode of that matrix is statically known to be 22. And we can do the same loop structure. We don't have to change anything else. So this is effectively an optimization. And here I've printed out the matrices as well. So this first one, you can see it's got a pointer. It's got the address of that pointer. This is a 32-bit because we got a pointer to floats. This is 22 by 19, strided by 1. These are just the default strides. It defaults to column major. A stride of 1, that's a suspicious looking underscore, and a stride of 22. If I make this mode static, then I can again print this matrix. You can see this underscore. The underscore is indicating that this value is statically known. So this mode is statically known to be size 22. This mode is dynamically known to be size 19. And now both strides are static, which is pretty cool. I didn't tell it the strides, right? This is the default column major strides. So default column major, we've got a static 1 stride and a static 22 stride, which means that when I index into this matrix, the inner product is not going to be the inner product with the stride. It can build in these statically known integers into the inner product. And actually, the compiler is very, very good about making that much faster than dynamic integers. And then, of course, we can specify the strides as well. So we can make an arbitrary shape. We can make an arbitrary stride. Those strides can be both dynamic and static as well, anything you want. And we can extend this to arbitrary affine layouts. Layout left is this default column major that I was telling you about. Layout right is the opposite. It's the default kind of row major. It reads from right to left instead of left to right. And then here I'm just explaining these static integers. So that's all well and good. And this is all kind of like one-to-one. You can do the equivalents in with std md span or pretty much any other tensor library. So nothing, well, except for the static int enhancement is pretty cool, I think. And other tensor libraries have their ways of doing this. I think this is very terse and easy to work with. Now we can get into kind of the interesting stuff, though. So in all my work with tensors, it is very common to be in a situation where I have, consider a 2 by 2 by 2 tensor, okay? I have a 2 by 2 by 2 tensor, so rank 3. And I've got its layout here. It's sized 2 by 2 by 2 and strided by 4, 1, 2. So that means that as I go across the row is strided by 1. So A, B, C, D. You can see A, B, and C, D are stored next to each other, etc. And follow the strides to figure out what the physical storage pattern is. It's very, very common to want to take a tensor like this and fold it into a 2 by 4 matrix. And in this case, we can absolutely do that. This is really cool. So instead, I can just grab that same pointer, right, and replace the layout. Replace the rank 3 layout with this rank 2 layout, and everything just works. This one mode is across the row, so A, B, E, F, and there it is, A, B, E, F in physical memory. Everything's happy. And this, and I was able to do this and publish papers on this to great effect, where pretty much where any tensor contraction can be mapped to a batched GEMM. And we do that by kind of like grouping the modes together. And so we can identify modes, group them together, call this the row mode now, call this the column mode, call this the reduction mode because it's repeated along here. The batch mode appears in all 3 of these tensors. And we can canonicalize this tensor contraction into a batch GEMM. And that's equivalent to just folding the tensor into a matrix and then passing it off to cuBLAS or your favorite BLAS library. The problem that always bugged me was the following. I can fold this tensor into a 2 by 4 matrix, but I can't fold the tensor into a 4 by 2 matrix. There is no stride that I can put here. So A, C, E, G, A, C, so that's a stride of 4, but then E is a stride of 2 away from A. And we actually went backwards, right? We went from A to C, backwards to E, and then all the way to G. So there's no integer stride here that will describe where my elements are stored down this mode. So this asymmetry bugged the crap out of me for a long time. Why can I fold it one way, but I can't fold it the other way? And this is preventing me from just using all these GEMM and BLAS libraries off the shelf to perform whatever tensor contraction I want to perform. So I went back to this work and said, oh, well, but we're just combining modes and identifying them as other modes. So let's do that. So if I, instead of trying to fold this as a 4x2 matrix, I know that I can actually embed inside of this mode more modes and actually keep track of, like, this is a matrix inside of this particular mode. That's kind of weird, but according to this inner product rule, like, this still works as long as I index into this matrix with the right coordinates. Right now the coordinates for a row are going to be two-dimensional, which is weird, but it works. According to this inner product, it's a nice little generalization, and it and we can see it just works. If we wanted to index into a 4x2 matrix this way, but I don't, right? Because if I had to index into a 4x2 matrix using these like coordinates as a row index, like, then it's not a matrix. It's not the same as if I were just treating a 4x2 matrix. Okay. I mean, we could use indices here and just internally, like, map this row index into this row coordinate and then perform the inner product, and that would work. And then if we squint our eyes and kind of forget about this like hierarchical shape that I'm doing, if we squint our eyes and use these integer indices for the rows and the coordinates, then it really is a 4x2 matrix. I can treat it in code exactly identically to a 4x2 matrix. That's kind of cool. That's really cool. But this still bugs me. This still feels like an asymmetry, right? The 2x4 view was really, really simple. The 4x2 view requires this like hierarchical shape and this row index transformation. What's actually happening? Why isn't this perfectly symmetric? And then you can take a step back and we'll say, oh, this 4 mode is actually a folded version of the other 2 modes. It's just that we recognized that the transformation from these index row coordinates, from the row indices to the row coordinates, and then the inner product with this particular column major stride is exactly equivalent. So this 2, 2, 1, 2 is exactly equivalent to 4, 1. The indexing is the same. The result is the same. So this top one is exactly equivalent to the bottom one. We can index both of these with raw indices. We can index the top one with a coordinate. But if I'm doing code, I'm just going to use raw indices. So that was really cool. And I'm like, oh, so this is all symmetric. I can fold any tensor I want into any matrix I want just by combining modes like this. And instead of trying to flatten, or we call this coalescing, instead of trying to coalesce all the modes, I can just keep them next to each other and perform these computations. So let's start formalizing this a little bit. How do we build up these types? So I'm going to call a shape. A shape is going to be this hierarchical tuple concept, and it's going to have ints. And we define this as saying a shape is an int or a tuple of shapes. So it's recursively defined like that. And for lack of a better term, this is a pretty cute definition. A stride is similar. For all intents and purposes, you can think of these as integers as well, but actually these can be anything that support inner products with integers. So this is, in mathematical terms, this is called an integer module. We are free to think of this as only being integers for the time being. You can do some really, really clever things by playing with your stride objects. But we do want it to be congruent with the shape. So we want it to have the same kind of hierarchical tuple structure here. And then a layout is simply a pair of these shape and strides. And we can map between these logical coordinates within the shape and then this index parameter. And then a tensor is just a pair of a pointer or an accessor and this layout function. And so any pointer you have lying around, it's an array, a pointer. We can have tagged pointers. We can have implicit iterators, for example, like out of thrust, transform iterators. Any kind of iterator you got laying around, throw it into a tensor. Now it's shaped and strided, and you can do kinds of things with it. So this is nice for a representational perspective, but
I apologize, Chris. Just a very newbie question. Like, isn't an iterator a form of stride, or did I miss this? Basically, the offsets at which you stride over is effectively like an iterator. I'm just confused what accounting and transform iterator actually are.
Yeah. So okay, let me tell you a story about iterators. In Cutlass 2x. Everything was implemented with an iterator. And the iterator abstraction is a poor abstraction for multidimensional linear algebra. Because you're embedding not only, because an iterator is jumping between memory points arbitrarily. And so in Cutlass 2.x, all of the iterators were bespoke implemented. And we had all of these complex layouts and patterns that we wanted to represent, and each one was represented completely independently. The revolution here was in replacing every single one of those iterators with this CuTe layout. So in this perspective, an iterator is just an array. It's a data. It's a random access thing where I can ask, hey, data backing, what do you got at index 5? Right? And that's all it is. An iterator should be dumb. You can start getting clever with it, but think of it like it's just
but not too clever, right? Because the composition of two affine iterators would still be an iterator. So I guess the abstraction doesn't let you do wacky stuff where you're going back and forth, presumably.
It does let you do wacky stuff.
Oh, it does let you. Okay, never mind.
Oh, but we're not going to talk about that.
Okay, I see.
Yep. Okay. And then, so this is a pretty compact representation. Again, all I need is an iterator, something that when I send it an index, it can look up in memory or whatever else it wants to do. It can give me back a value, as long as that value is consistent. It should be a consistent lookup. And then the really fascinating part is that you can start running with this really far, and you can create what I call an algebra of these layouts. Because these are affine, like Mark just mentioned, you can combine affine functions. And you can start asking, hey, what can I do with two layouts? I can concatenate layouts, certainly. I can functionally compose two layouts. And it turns out that the functional composition of two layouts is almost always another layout. I can take the right inverse of a layout and get another layout. I can take the left inverse of a layout and get another layout. I can take the complement. Complement's a weird definition. There is a notion of a product of two layouts. I can take the product of two layouts, which you can think of like I can replace every every element of one layout with a completely other layout. So a layout of layouts. I can form this, what we call divide of a layout. So I can split a layout into two according to all of the elements that are in another layout. And this starts to get really powerful really fast. So just to be clear though, and I don't want to jump into the algebra quite yet, but just to be clear, the shape defines these coordinate mappings, right? We can go from these one-dimensional coordinates to these logical n-dimensional coordinates to these logical hierarchical coordinates. And then finally, we take the inner product with the stride, and that gives us our physical storage index. We take that physical storage index, we ask our pointer, hey, what you got? And the pointer comes back and tells us our stuff, tells us our value. So a bunch of quick examples. Obviously, we have column major, we have row major. It's very easy to do a column major padded, right? That's just a different stride. Cutlass 2 had these column major interleave iterators, but what it was effectively trying to model was this layout, where it kind of goes halfway and then scoots back and then comes up and then goes back up at the top. So it's kind of two blocks. And then you can do this thing, which it doesn't even have a name. Like, why are we trying to name all of these things? Just tell me the layout and we'll go from there. But the point being is that all of these layouts can be interpreted as 4x8 matrices, right? And I can index into them like they are 4x8 matrices. And I don't necessarily care where all of the data lives.
So Cris, with the question here, like, could you literally just put your finger somewhere on this like tensor and like draw like randomly and it'll get like a total like and just build like arbitrary layouts? Like I'm just like trying to think about like what is possible to express versus versus not.
Yes, it is possible to express some really crazy bonkers layouts. I have lots of examples if you would like one. And swizzle layouts are even crazier. So here's a crazy one. Let's look at one. So this is iterators versus layouts. Okay. So recall again in Cutlass 2, all of these kinds of loops were implemented with iterators, which like take me from one block to the next block, right? And this is how it was implemented on the right here. If you want to write this code and you want to maintain this code, kudos. But we were able to replace every single implementation, and I did a count at one point, and there were something like I should have put the numbers in here. Something like 200 to 300 implementations of iterators spanned across 80 files, composing something like 30,000 lines of code, 40,000 lines of code. And, none of these iterators work with each other. They don't, you need this iterator with this computer, with that math. And when I partition it from the grid level to the thread level, then I need to only use that iterator. Anyway, it was a disaster. But the point is, you can replace all of that with, so this is a layout. You can see I've got a relatively complicated layout here. I've got this magical swizzle function, which is doing something funny that it turned out to be useful inside of the architecture. And then I can do this nice little tile to shape. I have this layout, and it appears to be, how big is this layout? This is 16 by 16 layout, right? If I take the product of these two shapes along these two modes, 16 by 16 layout. But I didn't want a 16 by 16 layout. I wanted a 128 by 64 layout. Oh, but I can do that because I can just take a 16 by 16 layout and just and now I've got 128 by 64 layout. And we can print this too, by the way. So just print LaTeX, and we get this nice little printout. Here's my 16 by 16 layout. I've tried to color it to be reasonable, but it's still not very reasonable. Point is, I would like to write this once and then forget about it.
I have a much simpler question after this digression, but the iteration order of a layout, there's always that like natural indexing from 0 to the size of the layout.
Right.
I guess like new question, is it always left to right increasing along an individual mode?
I mean, you can write your for loop however you want. If you're just talking about writing your for loop, you're welcome to write your for loop however you want.
The photo that I think the next slide. Would this just be like from left to right, exhaust the size of an individual mode, and then increment the next one?
If so normally what happens in applications, and we can get there in the next one. We're going to write algorithms with these tensors. But normally what happens, right, is I would have two for loops, one that's iterating across the rows, one that's iterating across the columns. And when I access that IJ pair, that's the value, that's the offset that I'm going to be looking up. That's all it is.
Cool.
So we have these slightly more advanced patterns. If you're familiar with Morton codes, this happens to be a 3-level Morton encoding expressed as a CuTe layout. This is an 8x8 layout. You can see that we have, I've alluded to these algebraic operations we have. So I create a small 2x2 layout. I take the product with itself to create a bigger one, and then I take a product again to create this 8x8 one. This is what it creates. Doesn't matter how I produced it. I could write this down manually, right? But it's cool to just take products of layouts and make things like this too. I can index into this in multiple ways. I can, like I said, I can treat this like an 8x8 matrix and index into it with row and column indices, but there's no reason why I can't also just use an integer coordinate. That'll get mapped to the exact same thing. I can use these hierarchical coordinates at any level of the hierarchy that I'm interested in. They all get mapped to the same position. These are all ways of asking for position 49. And of course, I can do matrix E things, and I can slice along logical subboundaries. So if I wanted the second column, this is how I would write that, and it gives me back. Obviously, this is not just a vector or anything. This is another tensor. It's got its own layout. We can figure out the pointer offset and the new layout, and go off and do whatever we need with the second column of this matrix. There are nice mathematical properties here. The shapes form a poset. So, for example, if I write an algorithm, and this particular algorithm requires you must pass me a 8x4 matrix, or in this case, you must pass me a 6x6 matrix. Then in principle, you can pass me any one of these as well, and that algorithm will be happy because I can index into a 6x6 matrix symmetrically for every single one of these tensors, which is really, really attractive. So I can start doing really clever, crazy things with where all of these values live and how they're being accessed. So like I said, this was a great success for representing everything that Cutlass ever wanted to represent, and more. So let's write some algorithms. This is cool. Let's write copy. If I want to copy from one tensor to another tensor. Okay, I've left a lot of space here. We probably need to consider the rank, right? So if the ranks are two-dimensional, then we need two for loops. We'll probably iterate over the rows or the columns at once, but we need to do that together. What about three-dimensional tensors? It gets a little harder. All of these tensors accept integer coordinates. And so that's my implementation of copy. And that's universal. That will work on any tensor in CuTe.
Is this considered like a natural ordering of a layout? Because like I guess, does every layout define this sequential index to the end? That's kind of what I was referring to, where in your previous slide you have this like iterating pointer movement. And I'm curious what the
little line was just for exposition. It just kind of shows you the physical order within this storage. But yeah, it doesn't have anything to do with necessarily the iteration order or anything. So this is interesting, pretty immediately interesting. We can start pointing out some problems. So copy is fundamentally, I would call copy fundamentally a rank 1 algorithm. Like, I do not care that you're passing me these super high dimensional tensors or anything. And what's most interesting to me is, again, remember the static versus dynamic stuff. For static shapes, this is optimal. And by that, I mean that if the shapes of these two tensors are both static, then this loop can be completely unrolled. The coordinate transformations that I have to apply can be also computed completely statically. And the inner product to get the physical offset can also often be computed statically. If the strides are static, then that will also be completely statically computed. If it's dynamic, it'll still be optimal because like I've got that hierarchical coordinate that I'm performing the inner product with. I know that coordinate statically. And the point being is that static shapes are extremely common, especially in CuTe programming, because RMEM, a register memory, is fundamentally static. Shared memory, we almost always know the layout of shared memory that we want to be computing with. Tensor memory in Blackwell is always static. And the first thing, and global memory, that might be a dynamic shape. But the very first thing we do to every global memory tensor when we are writing a CuTe kernel is we tile it. And that tile is static. So the subtile that we're working on within the block of our CuTe kernel is almost always a statically sized tile of global memory. So this starts to tickle you a little bit, and you can think about what you can do with this implementation. We can obviously copy one-dimensional arrays to each other. We can copy multiple dimensional arrays to each other. So this would be a rank 3 tensor copy. We can, gather a bunch of elements that are kind of distributed around away from each other. We can gather those all into a vector. We can do the opposite, scatter a vector into a bunch of elements that are scattered around everywhere. These are kind of interesting. Zero stride is a thing. I can broadcast. So this is a logically 8 element vector where every element of that vector is the same value in memory. And I can copy that to a non-broadcasted vector where every logical element is a distinct element. Similarly, I could copy a constant vector to another constant vector, or I could perform a transpose. This is an implementation of transpose. Copy is an implementation of transpose. And I can take an 8x3 column major, tensor and copy it to an 8x3 row major tensor. And this implementation of copy will just do all of these for me.
We got an interesting question in the chat. What is optimal with respect to in your last slide?
In the context of, I don't want any runtime overhead whatsoever. So I've suggested that we should be doing these row index computations and these inner products everywhere, everything like that. I don't want that to cost anything at runtime. And so long as the shapes are static, that almost certainly will not cost anything at runtime.
And I guess, Chris, another newbie question, which is like, Is this like the heart of the complaint regarding like slow compilation times? Like in effect, like especially when I looked at your slide 37, like you're generating like straight up like an algorithm that like, the alternative is someone having like like writing separate functions for them. And is this sort of like the source of the compilation problem, or is it like something else entirely?
Yeah, of course. It's propagating all the static information around, and I make absolutely sure that I never lose track of any static information ever, because that's the death of runtime. Right?
And related, like we had Ismail Maj ask a question, which was like, why templates and why not things like const expressions? Like again, forgive me, I'm not like a C++ expert.
It's the compiler is very, very bad at propagating const expr around.
I see.
There are very easy ways to lose track of const expr, and then all of a sudden you've got a dynamic value in your code. So.
All right. Last question for me. If you go to slide 37.
Slide 37. Yeah.
Next one. So things like, for example, like when I look at your 1D array, like copy versus transpose, like those seem to me like, oh, you can be clever algorithmically and do something, but like things like gather and scatter, like these are things like where like the math needs to touch like the real world.
Yep.
And so I'm curious, like there's kind of like what you can express, and then there's like what low-level APIs you need to call in the NVIDIA ecosystem. And I'm sort of wondering if you could help me. Okay, it sounds like it's coming later.
I can show you an example of that right now.
Okay.
So this is more of my CuTe copy stuff. We can talk about optimizations, but I don't want to get into that right now. Mm-hmm. But imagine I have a global memory tensor. First thing we do, we tile into it, right? I have very generic ways of tiling into it. For example, this is 4 different ways of tiling into global memory. I claim that every single one of these ways is a 4x8 subtensor, right? It's a 4x8 subtensor. It's just going to have different strides, whatever. Cool. Okay. Now here's the shared memory that I want to copy it into. Here's 4 different ways that I can arrange my shared memory. So I can define my shared memory layout, right? And I might want to define it one way or the other in terms of access patterns or vectorization or what have you. There's one way to copy these. No matter what I have, I can copy a 4x8 tensor to a 4x8 tensor. Any one of these tiling patterns, any one of these shared memory layout patterns, I'm done. So that's the reason why this is so powerful. And of course, there are optimizations that we can make inside of copy. And we can do those very well, in fact, because we can inspect the layouts and we can make deductions about what we can do better by inspecting these layouts and asking questions about like, where's the stride 1? Should I be iterating in this way or that way? Maybe I can vectorize elements automatically. Maybe I could prove that there are no race conditions. Maybe I can eliminate redundant instructions or do a lot of fancy things. Use more complex instructions to perform an equivalent copy. Same thing for GEMM. GEMM is fundamentally a rank 3 algorithm. This is my implementation of GEMM. And again, we can start using it for a huge breadth of applications. So all of the NT, TN, NN, TT BLAS GEMMs, obviously. I'm not going to list them all out, but they're just swapping LDA and 1 here in the layouts. We can do an NTT gem where I'm transposing the C matrix instead. Of course, you can do this in BLAS as well, but you got to use the transpose trick, and half the people probably don't know what I'm talking about, but it comes up at least a couple times a month in our Slack. The Bliss gem. Bliss is another BLAS library that uses arbitrary strides along both modes of the matrix. I always thought that was kind of interesting. It's cool. We get it for free. We can do tensor contractions, of course. If we have multiple modes, we can do a tensor contraction. Multiple M modes, multiple K modes, doesn't matter. We can do convolutions. Convolution's a little crazy. But IM2call fundamentally transforms a convolution into a matrix multiplication. We can represent the IM2call transformation with a CuTe layout, and then just call GEMM and you're done. And Of course, we have to make, proper optimizations, but the point being is that convolutions can be tiled the exact same way that GEMMs can be tiled, and in principle, we don't have to write lots of extra code for it. We can reuse the same optimizations and kernels that we've written for matrix multiplication. How much time do I have, Mark? Do I have a hard limit?
You can go as long as you like.
Really?
Yes. I've been really enjoying this. So if you want to go 3-4 hours, it's totally your choice.
Okay, let me get through this section then, and I'll stop after this section, and we can chat about where to go from there.
Mm-hmm.
So, wouldn't the TMA load be more useful than the universal? Yes, it would. If only we had a way of constructing TMA copies with CuTe. Yeah, we have lots of TMA examples with CuTe. So CuTe composition is the workhorse of the CuTe algebra. All of these products, divisions, tilings, they're all implemented with composition. I'm going to show you what that means. Let's go back to our layout mapping, how our layout mapping works. We transform our coordinates, right? And then eventually we take the inner product of those coordinates with the strides in order to get our physical index. If we squint or get a little drunk or whatever, then we can ignore most of that and say, oh, a layout is just a function from integers to integers. And the first thing I can think of to do with a function of integers to integers is functional composition. And it turns out that the functional composition of two layouts almost always produces another layout, R. And so I'm going to define I'm going to define the composition of two layouts, A and B, to produce another layout, R, such that R is shape compatible with B. This is my notation for shape compatible. This is that post set of shapes that I showed up here, right? I want it to be compatible with what I'm composing with, which is just a shape constraint. And then such that, we satisfy the composition property, where B of C evaluated at A is exactly what the composed layout gives you. So layout R is compatible with layout B, which means that all coordinates of layout B can be used as a coordinate of layout R. We have left and right identities, obviously. This gives you associativity. This gives you left distributivity upon surjectivity of B. Bunch of other cute stuff. Point is, let's suppose we have this composition function, okay? And let's do something interesting with it. So imagine I have a vector here, okay? I'm not going to tell you the layout of this vector or anything else. I'm not going to tell you where the data lives inside of this vector. I'm just going to give you a vector. This is input to your program, okay? And now inside of your program, you want to start partitioning this vector, okay? So for example, I want thread 0 in my CuTe program to be responsible for these 6 elements. Okay. So what I'm going to do is I'm going to create another layout which points to those 6 elements. And by points, I mean, like, I'm going to list the coordinates, not the addresses, anything like that, the coordinates. So this is coordinate 0, coordinate 1, coordinate 4, coordinate 5, coordinate 8, coordinate 9. I'm going to put those down in a list. And I'm going to say, hey, that's a layout. And I can represent that layout as 2, 3, 1, 4. So this is 6 elements strided by 2 and then strided by 4. I'm sorry, I want each thread to have these 6 values. I was doing it upside down. And then I want the next thread to have these 6 values. Okay, so again, I list out their coordinates. not their addresses. I haven't told you what the addresses are or anything like that, just their coordinates. And then we have 2 more threads lying around, and they get, I want them to have the values in these positions as well. Okay. So we've looked across the row here, and we've noticed that the values that each thread receives forms a layout. And now I look down the column, and I notice that the threads where each thread starts is also a layout. And I can write that layout as 2, 2, 2, 12. So I stride by 2 first, and then I stride by 12. I put these together, and I can create a 2-dimensional layout. Now, this 2-dimensional layout, what is this? What is this object? This is a map from my thread index and my val index to a 1D coordinate of my array. Right? So if I am thread 2, and I want the 4th value of that thread, then I'm looking at, then that thread value pair tells me I'm looking at coordinate 17, which is this one right here. Okay, that's a weird construction. And so now, but if I have composition, then I can take a vector like this. I can compose, functionally compose with this thread value layout that I have. I get another layout. Because the result has to be compatible with the layout that I compose with, then it's still 4 by 6. And if I want to partition it, then it's just a slice. So now thread 1 has all six values, these green values. This is thread 1's ownership. This is thread 1's subtensor of this vector. All 6 elements that thread 1 wanted, it now has. And so in code, it literally looks like this. I have a tensor of input, I create a vector, right? I have this thread value layout that describes this partitioning pattern. I literally call functional composition on the input tensor and my thread value layout. And then I slice it along the thread index that I'm interested in. So this thread now owns this row of elements, which is these 6 elements in the original tensor.
I have a quick question.
Yeah.
This makes sense. I'd say my curiosity question is, what if the thing you're partitioning isn't so well aligned? I guess, like, what's the general strategy for handling predication?
Predication is really cool. That would be an entire another talk. We have a formal and really strong approach to predication. So yes, you can compose. So just like, we need to tile tensors into tiles where the tiles don't perfectly divide the matrix or something like that. That is totally fine. You can still perform, all of that is implemented with composition, and composition will work. It will do exactly kind of what you think it is, which it will round up. But then you need this predication tensor to tell you which values are legal to access and which aren't.
Cool, makes sense.
And that's it. And
I didn't know mine.
There are magic and equally mathematical ways of constructing that predicate tensor that will always protect you. Yeah,
cool.
And so the moral of the story here is that given a layout, given a tensor, partitioning, the term partitioning is functional composition followed by slicing. And that's a pretty cool and powerful observation, because I can partition a vector like this in any way I want by just defining the right thread value layout or however else I would like to partition this kind of thing. And then the punchline. The punchline is we did this for a tensor, or for a vector, right? So we we constructed this thread value layout, which is a partitioning pattern. We applied that to a vector of elements so that each thread would get a portion of this vector. But every tensor is also a vector. We can index into every tensor with integer coordinates, and we can think of every tensor like it's a vector. Which means what we've just done is we've devised a way to arbitrarily partition an arbitrarily ranked, arbitrarily laid out tensor. And that is wildly, wildly powerful because we can immediately apply that to MMAs, tensor cores inside of CuTe. So for example, this is my favorite tensor core inside of CuTe. This is the Volta 8x8x4 tensor core. This is what inspired CuTe. This is the first tensor core that I printed out in this way using this LaTeX print. And I was like, oh, that's so cool. This is, if you read the ISO documentation, this is the partitioning pattern that is specified by the instruction. The instruction requires you to partition your input matrices so that thread 0 has a value 0 here, thread 1, thread 2, thread 3. Each one has 4 down. You can see this one's not even contiguous here. Thread 0 has these 8 elements here. The point is, these are the same thread value layouts that we just did our exercise on. And we can encode that as metadata to this instruction. This is the only thing this instruction understands. And so it needs to be part of the instruction's metadata in order for me to use this instruction. And we can do this for every single tensor core in the universe. So this is a generic tensor core, a generic SIMT multiply. This is a DP4A, which was the predecessor to the tensor core. This is the first Volta tensor core. This is the Ampere double precision 8x8x4 tensor core. Looks pretty similar. Different partitioning pattern for A and B, different partitioning pattern for C. We're getting bigger now. Ampere 16x8x8. This is for half precision values. Again, just recording and writing down the partitioning patterns from the ISO documentation into these thread value layouts. On Hopper, it gets a little weird because we have these shared memory descriptors that we need to construct. And the A and B tensors aren't even partitioned, but the C tensor is. Point is, we can construct these shared memory descriptors precisely because we can inspect the layout of the incoming matrices. We can validate that they have the right layouts, and we can construct the shared memory descriptor for you. So all of this is completely opaque. So just a quick rundown. This is what we call an MMA atom. When we have the raw PTX and the PTX metadata, we combine those into what we call the MMA atom. It can check all of these layouts. It can create what we call fragments. But point it even cooler, we can just print them. So we have these MMA atoms. Show me what you're doing. Print the LaTeX. It shows me this partitioning pattern. Cool. This is exactly the thread value layout that we were just talking about. The tiled MMA, we can multiply these essentially. So if I have this instruction, I've printed out a single instruction's worth, right? This instruction operates at a 1 warp level. I don't want a 1 warp level. I want 4 warps. I want a 2x2 layout of this instruction. And so I take a product of that layout with a 2x2 column major layout. This could equally be a 2x2 row major layout or a 4x1 layout, what have you. So now this is bigger and more complicated. But again, I can just print it, right? We can do fancy things, actually. We can actually permute the M mode, we can permute the N mode, and we can permute the K mode. and you still have an equally valid computational strategy. So this is an example of permuting the M mode. And what that does, it's hard to see, but it brings like the threads values next to each other. So it's slightly easier to design a shared memory layout that will have good access patterns for this MMA instruction. But effectively what this is doing, this is interleaving multiple MMA tensor cores, which is really amazing. Whoops, oh no. Finally, we can slice that, right? Each thread is going to need to access its particular data. So we take this giant tiled MMA that we've constructed, however we've constructed it, we pass it our thread index, and now I've got an object which represents the partitioning pattern for this thread is going to inherit the values in A, B, and C. I've highlighted thread 24 here. And you can see it doesn't even make sense, right? From a GEMM perspective, iterating over rows and columns and stuff like this one. What is this guy doing way over here? That's bonkers. I wouldn't want to keep track of this by hand. How do we use this? How do we use this MMA? We construct shared memory tensors. Again, these can have any layout that we want. We construct our MMA however we want. We get a slice of it, and then we can use that MMA to partition our shared memory. So we partition our shared memory, partition our shared memory, partition our shared memory. That gives us back our threads subtensor that it's going to be responsible for in this instruction. And then we also need fragments. So these are like registers. So these tensors are still shared memory. These tensors are register memory. These registers just have the same shape as the shared memory, which means that we can copy. So we copy from shared memory to registers. We copy from shared memory to registers. We clear the results accumulators. We can write a triple for loop, really, really basic, and call our really complex instruction. And then copy our registers back to global memory. This is global memory, not even shared memory, right? This one's global memory, GC. GC is global memory, SB is shared memory. But we partition global memory the exact same way that the instruction expects. And so the instruction doesn't care. It doesn't care if it's shared memory or global memory or what have you. So all of these are shaped right. So I want to stop there. And this is the basis of CuTe. And this is what made programming Cutlass much, much, much easier, because clearly we have a extremely robust, extremely general representation of these tensor cores. We can access all of these subtensors. We can always see what's going on. If we have a bug, we can just print out these tensors or print out these MMAs. Optimizing very often just becomes like figuring out the right shared memory layout so that this copy is fast, so that we can vectorize this copy internally. But otherwise, the MMA is just like, it's always right. It's difficult to write incorrect code when you adopt these kinds of patterns. So that was only 15 minutes over. I'm pretty happy with that.
You don't have to stop now, by the way. I think I could go longer if you're interested. But like maybe could you give us like some sense of what you're, because I still see you're like maybe a third of your way through your slides. What were like some other ideas you're hoping to go over?
I've got a lot of slides. There are just really cool things that we can do with this. Like I've already shown some pretty amazing results, in my opinion. But like, for example, returning the copy, right? We have all of these possible like inputs to copy. You can ask about vectorization. What if I wanted to copy, if I'm copying this layout to this layout? In principle, like instead of performing, these two values are next to each other in physical memory. Agreed? And these two values are next to each other in physical memory. So that means that I can perform a vectorized copy. I can issue one instruction of double the width instead of two instructions. And I can do that here for this blue element as well. The 24 and 25, I can slip into position 18 and 19. They're next to each other in physical memory. Next to each other in physical memory has nothing to do with next to each other in logical memory. So 0, 1, 2, 3, 0, 1, 2, 3. I can perform a four-way vectorization here in copying this tensor to this tensor. And that's because they have what we call a common sublayout. This one has a 2-element common sublayout. This one has a 4-element common sublayout. If only we could figure out what that common sublayout was. And I don't want to go too deep into it, but we can figure that out. We can start writing down the math for what exactly is a common layout. We invert that, and it turns into the inverse of one layout composed with the other layout. And that tells you exactly the overlap of those two tensors, and it tells you exactly the vectorization width that is safe to perform.
Is this like another overall theme in your work, which is like you're basically mathematically proving a priori at compile time which optimizations are safe to perform?
Yes.
I see. Okay.
Yes.
Driss?
No, I don't think it is. Another way to rephrase a common sublayout? Is it like the minimum slice that is contiguous?
Yeah. So when I actually present this and don't completely gloss over it, the question is, what even is a common sublayout, right? And so the simplest way to express it is that A and B have a common set of coordinates that map to consecutive offsets.
Makes sense. Yeah.
And so there must exist a certain set of coordinates where they both are producing the same consecutive offsets. And so there's multiple ways of writing that. Right, and then we can kind of play around with the math and the expressions here, and we end up at this really simple invert B composed with A.
I have a left field question, which I think the validity and power of CuTe for GEMM programming is very apparent. If someone at NVIDIA were to say, Cris, write me a kernel to do X, are you going to reach to CuTe to express the partitioning of the data to threads and values for any kernel you could think of?
Did you say if someone approaches me?
When?
Every single week, yeah. So yes, and I've reached for CuTe every single time. So for example, when we were trying to figure out how to program TMA, TMA is a very, very, very complex copy instruction inside of Hopper and Blackwell. Moving on. And it requires an immense amount from the programmer. But I was able to use these CuTe operations to... TMA has what's called the TMA descriptor, which describes the entire problem. And then you have to generate coordinates inside of that problem space, and TMA takes the coordinate and the descriptor and does all the predication for you, and it does the right thing, right? That descriptor is huge, and it's a pain in the butt to write, and it's confusing, and people get it wrong, and people don't optimize it quite properly. But I can inspect the global memory layout, and I can inspect the shared memory layout, and I can generate that TMA descriptor, and I can generate the right coordinates, and I can figure out where you are and how many bytes are going to be transferred, and blah, 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 blah. And everything is done for you, and it's very safe, and it's relatively easy to write.
That makes sense.
Yeah. So this kind of programming model has, yes, it's found a ton of applicability inside of GEMMs, but it's become more general than that, where we are using it for every copy operation, every compute operation, that we have. Copy operations are getting extremely complex. They're all collective. They're using multiple threads. They're using multiple warps. The source, the source partitioning pattern is not equivalent to the destination partitioning pattern. So this is a copy atom, which is the equivalent of an MMA atom, but for copies, right? And this is for LDSM, which is a load from shared memory into registers. This is the partitioning pattern for the source, which is shared memory. This is the partitioning pattern for the destination, which is registers. They are not the same. That's mind-bending, and it's impossible for humans. And we had Excel sheets on Excel sheets, like tracking shared memory layouts and operations, and what is this register representing, and where does this live, and how do I get this all back in the epilogue, back to global memory, and how do I make sense of this? But then at the end of the day, like, all we want to do is write code like this, where I have some kind of tiled copy. I apply that partitioning pattern to the source. I apply that partitioning pattern to the destination, and then I just start calling copies and trivial for loops over the integer coordinates of these tensors.
That makes total sense.
Yeah. So,
Cris, I want to ask you like maybe one dumb question, one interesting one. So the dumb question, considering I wish we had you for a bit longer, do you mind sharing your slides after this call? Like, just as I'll bet a lot of people want to go through them.
Yes, but I won't include all of them.
Okay.
I'll make a
whatever you're comfortable with. I guess like my second question is like, when I look at sort of like the annoying parts of writing PyTorch code, like at least the parts where people get tripped up the first time, it's like very often like when they're doing like reshapes and cats and flattens, and it's basically people are like manipulating shapes, and it's kind of like hard for them to sort of like mentally map in their heads.
Right.
But like it sounds like while for CuTe maybe the upfront overhead is like quite higher, like ultimately it gives you like a mathematical algebra for you to reason about, like copies, reshapes, regardless of layouts, regardless of the number of devices, etc.
Yes, and there's a lot to say about that, whether you're talking about like logical reshapings versus physical reshapings, and do you actually care where everything lives? Sometimes you don't, sometimes you do. There's lots of these extra questions, so you do have to be careful. But yes, in terms of just like being able to fold just the representation itself, and being able to fold tensors into matrices in more robust ways than are usually possible, has been immensely useful for just getting this stuff off the ground.
And so would you say like the two papers you linked there at the bottom, like did those age well? Do you still view them as sort of like the best intro for people to get introduced to these ideas?
Oh no, absolutely not. These are academic papers on applications for tensor contractions and such. If you want an introduction and you want further work for Cutlass and CuTe, go to NVIDIA Cutlass. There is an immense amount of media and documentation on the Cutlass. I have my own documentation folder. Most of these I wrote myself. And then the new Python DSL, you can see how to get started, the quick start here. Hello Worlds also goes through a lot of the CuTe operations, all of these products and divides, and how do I do tiling and predication and such and such and such and such. That is the best place to get started. There are a lot of code examples as well that you can find in here that are linked in within this documentation as well. All of those are highly, highly recommended for continuing and getting in there and like hacking on kernels and doing that one weird thing that you were never able to do before.
Okay, I think then this might be a natural time to call things. Cris, honestly, thank you so much. Like, this is one of my favorite talks so far on the server. The recording will be out, folks, soon. We'll hopefully get some slides, and if you like this, please comment on the video so Cris comes again. Next week, we're going to have a talk on disaggregated LM inference by Jindo Chen, and yeah, I'm looking forward to it, and see everyone soon.
Cool. Thank you, Mark.
Thank you.